Sound check, sound check. Looks like I can hear myself. What about video? Can I see my hand over there? That also looks good. All right, sound check complete. Let's put away the headphones and get started. And would you look at that, for once I actually do it on time. I know the past, 2-3 episodes have been delayed. But hopefully I'll be able to remain consistent with my schedule for the rest of this course. We'll see. I've looked over what we still need to get done, and I might end up doing some longer episodes to get through some of the topics. I mean, worst case scenario, going at my current pace, we would still be done before the AP exam, but I would prefer to be done sooner rather than later so that there can be lots of time for review and questions and all that. So I might either do some extra episodes here and there whenever I find the opportunity, or I will just do longer episodes, maybe an extra hour to get through some of the topics a little bit faster, just so that I'd like to have a full month at minimum of review time before the AP exams. That is what I would prefer anyway. But yeah, I'll keep thinking about it. I mean, today we're going to end a chapter for sure, because we only have a mini topic and the rest is just practice problems for today. All we're doing for today in terms of new stuff is introducing power, and there's not a lot that you do with power. There's not a lot that you can be asked about really in a mechanics-focused course. Maybe in electricity and magnetism it becomes a little bit more relevant, but, relevance isn't even the right term. It's just, there's a limited number of things that you could even be asked in a mechanics context when it comes to power. So, yeah, we'll just be breezing through the topic of power and then just doing some power-focused problems and then just some mixed review problems for the chapter as a whole, and next time will be the start of momentum, and we're probably going to get that done in 2 streams, because there's not too much to learn about momentum that isn't just kind of review of stuff that we've done before, force and energy and all that good stuff. Momentum is pretty easy once you know your force and energy. So that one is probably just going to take 2 episodes to get through. And then we'll probably spend, 2-3 episodes on circular motion and gravitation? But yeah, so plan for today is introduce the concept of power. Oh, and before I forget, I saw the footage from last time and realized I had a corner that wasn't showing up really well. So there was this page over here where I was defining mechanical energy. I don't think at any point in the previous stream I actually moved the paper up close enough for this to be visible. So if you were wondering what I had written there, now you know. So sorry about that, and I will try to watch for that in future streams, including this one. Okay, so then, power. What is power? Power is basically just the rate at which work is being done. Power. It is the rate at which work is being done. It depends on work, and just like work, it is a scalar. The rate at which work is being done. Oh, and I forgot those lights. Let me get those. There we go. The rate at which work is being done. So you can imagine what the equation for power is going to be. Power, I'm going to represent with a curly P, which I draw like this. The reason I don't use a regular capital P is because we're going to be using that for pressure for the last chapter of Physics 1. And the reason I don't use a lowercase p is because we're going to use that in the next chapter for momentum. So curly P is what I am going to use for power. And it is equal to the work done over the total time. And sometimes people write this as a delta T. It's whatever. It's the work done divided by the amount of time it takes to do that work. But work is force times displacement times the cosine of the angle between those two vectors. Work is the magnitude of force times the magnitude of displacement, I guess I'll call it delta x, times the cosine of the angle between those two vectors. And displacement over time, or change in position over change in time, is equal to what again? That is something we learned in previous chapters. That's velocity. So in fact, we can write this as force times the magnitude of the velocity times the cosine of the angle between their directions. Or in other words, if we wanted to write it in its most compact form, we could write it as F dot V. But this, of course, is assuming that you have a constant force and a constant velocity. For situations where force or velocity are varying with time, you might end up needing calculus. Or without calculus, I guess the farthest you could get is you could calculate average power. You could calculate average power by taking an average force, by taking the magnitude of an average force multiplied by some constant velocity, or you could have some constant force multiplied by some average velocity times the cosine theta. I'm just not writing it because usually we assume that the force and velocity are in the same direction for most of our power problems. But you could include that cosine theta if you wanted to. But yeah, apart from these two scenarios, if your force and velocity are both variable, then it's highly likely that you would need calculus to get any further, and for Physics 1, we are not doing that. Let me think. Is there anything else I want to comment on equation-wise? So I guess another thing we can do with this equation is we can rearrange it. So if you multiply both sides of this equation by time, then you can get power multiplied by time is equal to work. Power multiplied by time is equal to work. This is something that students tend to forget. The problem is that the units of power can get students confused on this. So the units for power, power is in units of watts. At least that's the standard unit, is in units of watts, named after, what was his first name? James Watt, if I'm not mistaken. And watts are represented with the symbol W. I don't like this symbol. If I do use it, I will give it serifs like this to distinguish it from the W that I use to represent work. But yeah, power is in units of watts, but a watt you can also figure out just from the equation for power. If work is in joules and time is in seconds, then that's joules over seconds. So what I prefer to call them is joules per second. And I feel like thinking of them as joules per second is better because it reminds you that you can multiply joules per second times the number of seconds to get your total joules. So it eliminates the confusion of the symbols. You don't have to guess if the capital W means work or watts. And it also just has this built-in reminder that if you multiply it by time, you get energy. So that's why I prefer to use joules per second instead of watts. If you deal with power in the real world, a lot of times power is expressed in terms of horsepower. You've probably heard of the horsepower of things like a car motor or whatever. Horsepower. Horsepower. Represented with the symbol HP. 1 horsepower is approximately equal to 746 watts. Or 746 joules per second. Of course, some people will say 745.6 or 745.7 or whatever, but 746 is good enough for me. If your teacher has a preference here, then just stick with whatever your teacher prefers. But as far as I'm concerned, 746 is good enough. I mean, it was never really exactly defined anyway. It was called horsepower because back when the concept was first created, it was meant to be a rough measurement of the power output of the average horse dragging ropes and whatever. So yeah, not a very precise definition. It didn't have a very precise definition from the get-go, so I'm kind of loosey-goosey on the definition of how many joules per second 1 horsepower actually is, but according to Google, it's, let me see, what was it? 745.7 is the first Google search result that I'm getting. But yeah, details. Worry about it more when you end up working for NASA, although honestly, if you end up working for NASA, they will probably just do it in joules per second anyway. Horsepower is more for the common man than it is for physicists. Anything else? I guess one more thing is you probably come across, rather than watts, you probably come across kilowatts, which is just 1,000 watts, the same way that a kilogram is 1,000 grams and all that. So you've got kilowatts. 1 kilowatt equals 1,000 watts. 1,000 watts. Or, again, as I like to think of it, 1,000 joules per second. And another related quantity that you might come across if you've ever looked at your electricity bill is the kilowatt hour. 1 kilowatt hour. kWh. Is 1,000 joules per second times 1 hour is equal to 1,000 joules per second times 1 hour is 3,600 seconds. So that's 3,600 times 1,000, so 3.6 million. Joules. The seconds would cancel out and you would just be left with joules. This is how electricity companies usually try to measure how much electricity you've spent, and they charge you by the kilowatt hour. And the last time I calculated it, which was before all the COVID inflation, 1 kilowatt hour of electricity was about, I think it was like 15 cents in my area. Oh, and by the way, even though you're not studying electricity and magnetism, in case you are curious about how much energy your devices consume, if you read them, then somewhere written on the devices you will find the amperage, that is the electric current, so amperage, how many amps. This is in units of amps or amperes, where 1 amp is equal to 1 coulomb of electric charge moving through the circuit per second. And then if you know the voltage, voltage, that's an L, not a T, voltage, in volts. I like to also use serifs on my V for volts for similar reasons, because the capital V can be confused for volume, but that's for the electricity and magnetism students to worry about. So voltage in volts, 1 volt is equal to 1 joule of energy per coulomb of charge, If you multiply coulombs per second by joules per coulomb, the coulombs cancel out and you're left with joules per second, or watts. So amperage, or current, multiplied by voltage is equal to wattage, how many joules per second your device consumes. And if you don't see the voltage written on your device, then that's probably because it's a device that just plugs directly into the wall, in which case you're just going to have to look up what that is for your country. Here in the United States, it should be 120 volts. And yeah, you can use that to actually calculate the electricity bill. If you figure out how many watts it consumes, and then figure out how much time you run the device for, then divide by the cost per kilowatt hour, or rather multiply by the cost per kilowatt hour, convert it to kilowatt hours, and then multiply by the cost per kilowatt hour, and you will end up with whatever it costs to run that device for whatever time that you actually ended up using it. But yeah, that's some of the more interesting stuff that you can do in the electricity course with power. As far as mechanics is concerned, we don't really get to do anything that exciting. But yeah, those are some power-related concepts that you might come across here and there. So yeah, let's do some problems. Let's open up my book and see what we've got. There isn't that much, if we're being completely honest. Let's see, power. Okay, so first one is pretty straightforward. It says a skier of mass 70 kilograms is pulled up a slope by a motor-driven cable. Part A, how much work is required to pull him 60 meters up a 30-degree slope, assumed frictionless at a constant speed of 2 meters per second? And then part B is asking what power must a motor have to perform this task? Really straightforward. Oh, let me go ahead and I can already see my paper is a bit off position. There we go. Okay, so a skier of mass 70 kilograms is pulled up a slope by a motor-driven cable. They said it was a 30-degree slope, and then the skier over here has a mass of 70 kilograms, and they are being pulled up. Let me use a different color for this. They are being pulled up by some motor-driven cable. So part A, how much work is required to pull him 60 meters up a 30-degree slope? So I guess I'll call it delta S equals 60 meters. And the slope is assumed frictionless, and it's also pulling him up at a constant speed of 2 meters per second. So speed equals 2 meters per second. Well, if you know the mass and you know the displacement, then that's really all you need, and you assume that this is happening on Earth. So work being done on him. Well, if he's being pulled up at a constant speed, then we know that the net force on him must be 0. So really, we just need to figure out what the tension force pulling him up is supposed to be. Him or her, they never really specified, but we've got force of tension this way. Normal force, which isn't going to do any work because it's perpendicular to the displacement at all times for this scenario. And then we've got the force of gravity straight down, which I guess in this case we actually do want to break into components. So that's going to be force of gravity cosine 30 degrees, and then downslope we're going to have force of gravity sine of 30 degrees. Well, I guess another way we could do this, if the person is going to be moving at a constant speed, then that means that their change in kinetic energy is 0. So what we could do is we could just set the total work equal to 0 and solve for the force of tension by first figuring out the work done by tension by subtracting out the work done by gravity. So there's more than one way to go about this problem. In fact, you could also use just conservation of mechanical energy, or rather it's non-conservation in this case, and use that instead. You could figure out if you're going 60 meters diagonally like this, then how far are you going up? You could figure out the change in height and then use that to calculate the change in potential energy, and you know the change in kinetic energy is 0 because constant speed. And so you would just figure out whatever the change in mechanical energy is, then it must be due to the work done by the tension force, because the only other non-conservative force is the normal force, and that's not doing work. So all the non-conservative work must be due to tension. So yeah, multiple ways you could solve this. And I would definitely recommend trying to do this in multiple ways, just so that you can compare all the different methods and decide for yourself what works best for you, but also just to give yourself confidence in the answers you're getting. If you're getting the same answers in more than one way, then that can give you more confidence that you're doing things right. And if you're not getting the same answers, well then, I guess you might need to do some review. But at least you would know that you need to do some review, and you would find out sooner than, the night before a big exam. Anyway, that's enough rambling. Let's continue. So, I'm just going to find force of gravity sine 30. Sine of 30 is conveniently 1/2. So, 70 times 9.8 times 1/2. Force of gravity on this person is 70 times 9.8. And then 70 times 9.8 times sine of 30 is just going to be half of that. So 70 times 4.9. Or 35 times 9.8. Either way, I'm getting 343. So this is 343 newtons, which must mean that the tension force must also be 343 newtons. Okay. So force of tension must be 343 newtons, since the net force has to be 0 for the speed to be constant. Well, the correct phrasing is that the net force has to be 0 for the velocity to be constant, and since the speed is constant and the direction is constant, that implies that the velocity is constant. I know maybe I'm nitpicking a little bit too much here, but the difference will become important in a number of scenarios, so we should be remembering to be specific about that. Okay, so now that we know the force of tension, we can calculate the work done by this cable's tension. Work done is going to be the force of tension times the displacement, at least their magnitudes, times the cosine of the angle between their directions. This is going to be, I guess I'll call it alpha here, so as not to confuse it with this. This 30 degrees, I guess we will just call theta, as we usually do, and I'll just say alpha is the angle between the force of tension and the displacement. Force of tension is up the slope, and displacement is also up the slope, so alpha would be 0. So you'd have 343 times 60 times cosine of 0. Cosine of 0 is 1, of course. We've seen this song and dance how many times now? We already know all this. Just multiply 343 and 60, and we get 20,580. 20,580 joules. And that's part A. Part B was asking, what power must a motor have to perform this task? Part B is asking, what power must a motor have to perform this task? Well, now that we know how much work needs to be done, we've got two options. We can either figure out how much time it takes for this work to be done and then divide by that time, or we can use the other form of the power equation. So we can either use work over time or force times velocity. The cosine is already accounted for. It's cosine of 0, which is 1. So we don't have to worry about that anymore for this problem. So yeah, we can either do total work over total time, or we can do force times velocity. The force in question, of course, this is the power output of the motor, which is pulling the cable. So this is the power we associate with the tension force specifically. We're specifically talking about the power that is associated with the machine that's generating the tension force pulling the skier up. Otherwise, the net power would actually be zero if you threw gravity into the mix. So, looking at this first method, work over time, we already have the work as 20,580. To calculate the time, we know that this person went up 60 meters at a rate of 2 meters per second. So you can say that 60 meters multiplied by, let's see, 1 second for every 2 meters. Meters cancel out. 60 over 2 gives you 30 seconds. So you can get time equals 30 seconds from there. And 20,580 divided by 30. 20,580 divided by 30 gets you 686. Gets you 686 watts, or 686 joules per second. So that's one method. The other method is force times velocity. The velocity is going to be 2 meters per second up the slope, and the force of tension is 343, so we could do 343 newtons multiplied by 2 meters per second. And that gives us 686 Newton meters per second. We already know from previous episodes, what was it, 2 streams ago, was it, that a Newton meter is a joule. At least for the time being. There's another type of Newton meter that we will see later that is not a joule, but that's because it's a different kind of multiplication. We'll talk about it when we get to it. But for now, yes, Newton meters are joules. So yeah, both methods work. It's really just, what do you find easier? And I would argue that multiplying by 2 over here was the easier way to go about it, but anyway, that is the end of that problem. Let's take a look at another one. While running, a person dissipates about 0.6 joules of mechanical energy per step per kilogram of body mass. Oh boy, so now they're throwing a bunch of units at us that we're not used to dealing with. And this is the type of problem that can throw off even some of the better physics students, because the sad reality is that a lot of students don't, even the best ones, sometimes don't stop to think about anything beyond what their teacher gives them. So this could throw you for a loop. But really, if you're good with your dimensional analysis skills, then this shouldn't be too bad for you. So it says, let me reread it from the start. It says, while running, a person dissipates about 0.6 joules of mechanical energy per step per kilogram of body mass. If a 60 kilogram person develops a power of 70 watts during a race, how fast is the person running? And it also says, assume a running step is 1.5 meters long. So really the challenge here isn't anything to do with the energy concepts, and it's more about just keeping track of all these units and making sure that you can work with this new thing. And this, you could argue that it's unfair, but in the world of science, sometimes you're going to have to look at, new ideas, new concepts like this that have never shown up in a textbook for you before. Well, I guess this one is literally from a textbook, but you get what I'm saying. You might have to read somebody's research paper and they might define things in this way, where they measure something per step, per kilogram, or whatever. And you're going to need to be able to find a way to grapple with this. So let's see. Writing down what they gave us. So they said a person dissipates 0.6 joules. 0.6 joules per step, and also per kilogram of body mass. And then they said mass is 60 kilograms, and the person develops a power of 70 watts. Power equals 70 watts, or as I like to call them, joules per second. And the question is, how fast is the person running? And it says, assume one step is 1.5 meters long. Okay. So we know the power. We want to get, so what we're trying to get is speed, the magnitude of the velocity, in meters per second. That is our goal. So we need to rearrange all of our units here to get them in terms of meters per second. So I've got joules per step per kilogram. I've got a way to convert steps into meters. So that's the first part of what we're trying to look for. We want meters on top. And we want seconds on the bottom, and my seconds are going to come from power, which is in joules per second. So I think I actually want to start with my power. So I think I want to start with my 70 joules per second. And let's see what we can do with that. The only other thing I have that involves joules is this thing, what was it even called? I guess we would call this, I don't know, energy consumption. There isn't really an official physics term that I know of for this. I'll just call it energy consumption for now. There's probably a better word that one of you guys can come up with for it, but energy consumption is what I'm going to call it, and I can't even fit it in there without making it look really horrible. But you know what I was trying to write. So I'm actually going to take the reciprocal of this. So for every 1 step times 1 kilogram, 0.6 joules are consumed. That cancels my joules, and now I've got these step kilograms to deal with. I can get rid of steps because I know 1 step is equal to 1.5 meters. So 1.5 meters on top equals 1 step on the bottom, and now I've gotten rid of steps, and I have meters on top. And now I just need to get rid of my kilograms. So just divide by the 60 kilograms. That is the person's mass. So just multiply by 1 over 60 kilograms. And there we have it. Right? 60 kilograms over 1 with no units, or the 1 with no units over 60 kilograms. So that cancels my kilograms over there, and I'm left with 70 times 1 times 1 times 1.5 over 0.6 and also over 60. Kind of crude, and I'm sure it makes some people uncomfortable, but that is what you have to do. So 70 times 1.5 divided by 0.6 and also divided by 60. And that gives me 2.91, and then repeating sixes. I'm just going to call it 2.917 meters per second. So I suppose one thing you could do, if you feel like it would be more comfortable, is take this energy consumption thing and turn it into consumption per meter, joules per meter. So multiply it by 1.5 meters, or no, hold on. Multiply it by 1 step over 1.5 meters, so divide it by 1.5, and that gets you joules per meter per kilogram, and multiply it by the 60 kilograms, and now you've just got joules per meter. So I guess I would do kilograms first. Multiply by 60 kilograms, and you would get 36 joules per step. And then 36 joules per step is 36 joules per 1.5 meters, which is 36 over 1.5 is 12, right? 36 over 1.5 is 24. 36 over 1.5, is 24. So that would be 24 joules per meter. And then from there, you would still have to do some dimensional analysis in order to rearrange it into meters per second. But that might be a little bit more, palatable to some people if you're not used to thinking in this way. Although really you should be comfortable with this kind of thinking. We're going to see something like this in the upcoming chapter as well. There's going to be a problem or two in momentum where we're going to run into something in units that we're not used to dealing with, but you can still work with them just fine if you look at things from a dimensional analysis perspective. So yeah, this was less of a power problem and more of a dimensional analysis problem. Off to our next one. Which one do I want to do next? Let's see, this one says electric motor accelerates the train from rest to that speed in that amount of time. Total mass is that much. Find the average power delivered to the train during its acceleration. Okay, I guess we can do this one real quick. It's not the most exciting problem, but we can do it. So, electric motor of a model train accelerates the train from rest, so V initial is 0, to V final equals 0.62 meters per second. And that happens in 21 milliseconds. Time is 21 milliseconds, which is 0.021 in seconds. The total mass of the train is 875 grams. So mass equals 875 grams, which is also 0.875 in kilograms. Find the average power delivered to the train during its acceleration. Find the average power. Here we have to use average power. I guess I would also just use the bar symbol for average. That's what we used before. Either symbol is fine. But yeah, in this case, we're going to assume a constant acceleration, which would also be assuming a constant force. And our velocity is definitely variable because it goes from 0 to 0.62. So we're going to have a constant force and a variable velocity. We're going to just replace our variable velocity with our average velocity. If we're assuming a constant acceleration, then the average velocity for constant acceleration is the average of the starting and final velocities. You might remember that from kinematics, and if you don't, then it might be time to review that. Average velocity is equal to v initial plus v final over 2 under constant acceleration. So that's going to be 0 plus 0.62 divided by 2. That's going to be 0.31. That's going to be 0.31 meters per second. Okay, and what is the force? Well, we know what the mass of this thing is. So if we can figure out what the acceleration is, then we will have the force. Net force on this object is equal to its mass times its acceleration. The mass is 0.875 kilograms. The acceleration we don't know yet, but we can figure it out through kinematics. We can figure it out through kinematics because we know v initial, v final, and time. We can just use the first equation of kinematics. V final equals v initial plus acceleration times time. 0.62 equals 0 plus acceleration times 0.021. 0.62 divided by 0.021 is going to be what? Approximately 30? 0.62 divided by 0.021 is 29.524 approximately. Acceleration equals 29.524 meters per second squared. So go ahead and plug that in here. And let's see what we have. 0.875 times 29.524. I'm getting 25.8335. I'll just round it to 25.83. About 25.83 newtons. And now we've got everything we need. Average power is going to be about 25.83 multiplied by 0.31. 25.83 times 0.31. I'm getting 8.0073. I'm just going to round it to 8.00. 8.00 joules per second, approximately. And there we go. If we wanted to do it as work over time instead, what we could do here is, let's see. So the net force, I guess I should have commented on this while I was doing this calculation over here. So the net force would have to be just the force of whatever is pushing this model train forward. I'm assuming there's no friction here. I'm assuming no friction, because if there is friction, they would have had to tell us some information in order to account for that. And the only other forces that would be acting on the train, if it's like on a track on a table, it would have to be normal force and gravitational force, which cancel each other out. So yeah, net force would just have to be the motor's force pushing the train forward. So that would also be the force doing the total work. So if you wanted to calculate it the other way, if you wanted to calculate average power as total work over time, then what you could do, I guess you would have to still do kinematics to figure out the displacement, but the force would still be this 25.83. So it would be, actually, no, you don't even need to do that. You don't even need to do that, because if this force is equal to the net force, if it's the only force that is left without canceling out, then that means the work it does is equal to the net work. And the net or total work is equal to the change in kinetic energy. So yeah, actually you don't need to do kinematics this time, because for the change in kinetic energy, all you would have to do is 1/2 mv final squared minus 1/2 mv initial squared. So 1/2 of 0.875 times 0.62 squared minus 0 squared for final squared minus initial speed squared, all over the total time being 0.021. And since we've already written it out, we might as well put it into our calculator and see if it gets us approximately the same result. There might be some differences due to rounding, but for the most part, it should be the same. 1/2 times 0.875 times 0.62 squared, all divided by 0.021, and I'm getting 8.008333. So yeah, approximately 8. Oh, I guess 8.0073 is what I got before. Okay, if I'm rounding to 2 decimal places, I should have rounded to 8.01, not 8.00. My bad. But yeah, up to 2 decimal places, they are approximately the same result. 8.01, did I say meters? Joules per second. They both give you 8.01. One of them is 8.007 and the other is 8.008. So after 3 decimals, you start to see differences between the 2 methods, but within 2 decimals, they get you the same result, which is reassuring. Okay, so there was that problem, which was fairly straightforward. Now this next one says, an electric scooter has a battery capable of supplying 120 Wh of energy. Wh, what is that? Well, we talked about it earlier. Kind of. We talked about the kilowatt hour. A Wh is a watt hour, and I would have liked it if the book had actually put a dot or a dash between the W and the H to make that more clear, but unfortunately they didn't do that. They just wrote WH all put together with nothing in between. And it is what it is. So the battery is capable of supplying 120 watt hours of energy. Watt hours are units of energy. It's units of watts, which are energy per second, multiplied by hours, which is a unit of time. So energy per time times time is just energy again. It's just really awkward because you've got mixed time units. You've got energy per second, and then you're multiplying by a time that is in hours. So convert your hours to seconds, and that issue gets resolved. Let's see. It also tells you just straight up, note that an energy of 1 watt-hour is equal to 1 joule per second times 3,600 seconds equals 3,600 joules. So they did it for us. So 120 watt-hours. I like to put a dot between the W and the H. Is the total energy, is the, I guess, battery capacity, you could say. And they tell us in the problem itself that 1 watt-hour is equal to 1 joule per second times 3,600 seconds equals 3,600 joules. And so it says, if frictional forces and other losses account for 60% of the energy usage, if 60% of energy is lost to friction, etc. Is lost to friction, etc. Not permanently lost, it's just lost in the sense that it transforms into heat energy and just goes off into the realm of the microscopic, turns into vibration energy at the atomic level that we don't really get to see on the big scale that would be noticeable to the human eye. If frictional forces and other losses account for 60% of the energy usage, what change in altitude can a rider achieve when driving in a hilly terrain if the rider and scooter have a combined weight of 890 newtons? If the force of gravity is 890 newtons, then what is delta H maximum, basically, is what they're asking. So this one shouldn't be too hard. We just need to figure out how much energy we have. Come to think of it, power doesn't really factor directly into this at all. All we really used were the units of power over here to get this watt-hour thing. So yeah, it's not really a power problem. I guess this just goes to show that there isn't that much variety of things they can ask you regarding power. I guess this just helps illustrate the point that I was trying to make at the start of the stream. There's not a lot you can do with power. In terms of problems anyway. In terms of practical applications, we use power all the time. So let's go ahead and figure out what this 120 watt-hours is. 120 watt-hours multiplied by 3,600 joules for every watt-hour. 120 times 3,600 is 432,000. So let me actually switch colors here. How about pink? So 120 watt-hours is equal to 432,000 joules of energy. And then some non-conservative work is being done. So they said 60% of this energy is lost to friction. So work non-conservative is equal to 0.60, that's 60% of the total of the 432,000. And if I go ahead and do that multiplication, what do I get? 432,000. I'm getting 259,200 joules. So now we can say that the kinetic energy initial plus potential energy initial of the bike or scooter, whatever it's called, plus the non-conservative work is equal to, oh wait, actually, since this is lost, it would have to be a negative. Since it's lost, it would have to be a negative. I have to actually assign that myself. Is equal to kinetic energy final plus potential energy final. So this scooter, if I had to draw it, so here's a person and they grab their little scooter, here are its wheels and all that, and they try to climb up some sort of hill. And the question is, how high basically can they go? What's the highest that they can go? The highest they can go would mean that their gravitational potential energy would have to be maximized. We would have to give them as much gravitational potential energy as we possibly could to get them to their maximum height. So we would assume that they start from rest. That's a reasonable assumption. And we can set potential energy initial. We can say that this height, we can say that's the h equals 0 line. And then somewhere up here is their h equals h max line. So this we can set to 0. And we're left with wait a minute. I feel like I did something wrong here. The non-conservative work. Wait a minute. So that's some non-conservative work being done, but what about this? This would have to be the total work. This would have to be the total work, which is, so 432,000 joules of, I know what I'm supposed to get. I'm just trying to figure out what the reasoning should be. And perhaps I'm overthinking it. So, if the scooter starts from rest and basically starts with no mechanical energy at all, then I have to add energy to the system in order for it to gain height. So a negative non-conservative work doesn't make sense. Okay, actually, what my non-conservative work should be, my work non-conservative should be this 432,000 joule total minus the 259,200 joules lost to friction and whatnot. So actually there's two non-conservative works. Yeah, that's what I messed up. So I guess this is non-conservative work due to friction, and then there's also 432,000 joules of non-conservative work due to just the motor of the electric scooter. That's positive, and the total non-conservative work is the positive work from the scooter minus the work done by friction and air resistance and other such forces, leaving you with a total of, let's see, 432,000 minus 259,200 is 172,800. Okay, there we go. So you get 172,800 joules of energy added or converted into kinetic and potential energy from, I guess, electric energy stored in the battery of this scooter, equals the kinetic energy final plus potential energy final. So kinetic energy final plus potential energy final is going to be mgh. Mg is 890 times h final, or h max. Now, we want this to be as high as possible. So if I do 172,800 minus kinetic energy final equals 890 h max, we're asking what is the highest this can possibly be. And in order for this to be as high as can be, the left-hand side needs to be as high as can be. And the lower the kinetic energy final is, the higher this left-hand side will be. So what is the lowest kinetic energy final that I can have here? In this case, it would have to be 0. Now, some people might say, well, shouldn't we always set it to 0 in these kinds of situations? And the answer is no. Sometimes you just can't set it to 0. In this case, we can, because this person is climbing up a hill and they can get to a point where, as long as they have some speed, they can continue moving up the hill until they come to a momentary stop, at which point they will probably just roll back down due to gravity. And that's a situation where they actually can do that. But what if this person instead went off of a ramp? What if this person instead let me draw their scooter again. I didn't plan this out very well. What if they went off of a ramp and then just shot into the air like this? Once they're in the air, they have no way to alter their horizontal speed. So once they reach their maximum height in a situation like this, they have to, at minimum, have enough kinetic energy to account for the horizontal component of their motion, which they're no longer able to change because the only force acting on them is gravity, which can't really touch the horizontal part of their motion. So yeah, you're not always going to be able to get away with just setting the kinetic energy final to 0 when trying to maximize height. If something is fired straight up, or in this case, something is moving along a surface that can exert a normal force at an angle and giving you some way of modifying your horizontal speed, sure. But in situations where that's not possible, you're gonna have some kinetic energy final no matter what. And the best you can get, the maximum height will be lower in those kinds of scenarios. But yeah, this scenario, we absolutely can create a situation where the person comes to a momentary stop at some maximum height. So kinetic energy final being set to 0 is perfectly fine. Now we just divide and we're done. So 172,800 divided by 890 is 194.157. I'm getting H max equals 194 point, I'll round it to 194.16 meters. And I guess if you want to be particular about what I called delta H max in the beginning, that would just be H final, or H max, minus H initial, which we set to 0, which is the same 194.16. So there you go. Now let's take a look and see if we have any other ones. I know there was one really good one to think about in the other book. I may want to actually look at that one next. Let me think. First, let's read these other ones and see if there's anything important to gain from them. So this one says we've got a card that starts from rest. Uniform acceleration, okay. And they want us to assume some sort of constant air resistance and find average power developed by the engine and instantaneous power of the engine at a specific time. Okay, I guess we can talk about instantaneous power. I mean, it's not really that complicated. If average power is force times average velocity, or average force times velocity, then instantaneous power would just be whatever the force is at a specific moment in time multiplied by whatever the velocity is at that specific instant in time. And that's really all there is to it. I don't know if we want to do a whole problem for that, though. Why not? Let's see if we can squeeze it in here. So it says a 1,500 kilogram car, and is everything showing up on screen well? I gotta keep checking for that. So we've got a 1,500 kilogram car. That starts from rest and accelerates uniformly to 18 meters per second in 12 seconds. So V initial is 0, V final is 18 meters per second, and time is 12 seconds. Acceleration is 1.5. If you use the first equation of kinematics, V final is 18 equals V initial plus acceleration times 12, so 18 over 12 is 1.5. So we get an acceleration of 1.5. We'll see if there's anything they want us to do with that. It says, assume that air resistance remains constant at 400 newtons during this time. Okay, so this acceleration is despite a 400 newton air resistance. Find the average power developed by the engine. Okay, there might be something of interest in here after all. Okay, so here's your car. There's going to be some force pushing it forward from the engine. And there's going to be some force resistance of 400 newtons from the air. I suppose I need to draw a window for this car. There we go. And of course you've got normal force and gravitational force, which cancel each other out and don't really do anything beyond that. And there's no friction that they mentioned. I guess maybe it's accounted for in this 400 Newton air resistance. But no friction was mentioned. So it says find the average power developed by the engine. Very important to take this air resistance into account for that. So they want, what is the average power? I guess I'll just write the word average since I don't have room to properly show the bar above the P. Power average of the engine specifically, due to the force created by this engine, and the instantaneous power at t equals 12 seconds. P instantaneous at 12 seconds. Okay, so like I said earlier, acceleration should be 1.5 meters per second squared. We can just use the first equation of kinematics to do that. I guess I can do it up here real quick. So V final is 18 equals V initial is 0 plus acceleration times 12. 18 over 12 acceleration is 1.5 meters per second squared. And now that we know the acceleration, we can do net force, which is going to be force engine minus the force of resistance minus the 400 is equal to mass 1500 times acceleration, which we now know is 1.5. And so that gives me 1500 times 1.5 is 2250, and then add 400 to that, and that's going to be 2650. So the force of the engine is equal to 2650 newtons. And the average power, so this force is constant, which means we need to use an average velocity, right? The choices for average power are a constant force times an average velocity, or a constant velocity times an average force. Since our force is constant, we must average our velocity. And since we have constant acceleration, the average velocity is just the average of the velocities. 0 plus 18 divided by 2, so that's going to be 9. So 2650 times 9. Power average is going to be 2650 times 9 equals whatever it is, approximately, what, 24,000 or something like that. 2650 times 9, 23,850. 23,850 watts or joules per second. Okay, what is the instantaneous power? For that, you would just use the force times the instantaneous velocity. So 2650, because it's 2650 at all times, multiplied by the velocity at 12 seconds, which is the 18 meters per second. So P instantaneous at the 12-second mark, is that visible on the screen? Yeah, there it is going to be 2650 times 18, which is going to be, what, 47,700? 2650 times 18, yep, 47,700. See, what I did was I just mentally tried to double the number that I got over here, because 18 is just 2 times 9. I'm sure some of you already noticed that, maybe sooner than I did. But yeah, there you go. So there's that problem. What about you? We have an elevator. It starts from rest and moves up. Okay, all that. No, I don't think there's much point in covering that one, so let me grab the other book and find that one question. I mean, I think I remember the essential parts of the question, but I want to make sure that I actually have the whole problem statement in front of me in case there are any aspects of it that I'm forgetting. But it was comparing two scenarios which might look like they lead to the exact same outcome until you think about it for a couple seconds and realize a certain something. Okay, I think it's somewhere in here. Okay, yeah, this is the one. And do I have a... no, new sheet. Backside of that sheet is already filled. Okay. So it says, 2 cars are at a stoplight. When the light turns green, the car of mass m begins to move with an acceleration of a. The car of mass 2m moves in the same direction with acceleration a over 2. Which car engine delivers the most power? So we've got 2 cars. One car has a mass of m and an acceleration of a. The other car has a mass of 2m, but an acceleration of a over 2. So twice the mass, but half the acceleration. And the question is, which car engine delivers the most power? Oh, and I forgot to draw wheels on this thing. That's not good. I mean, the AP exam is probably not going to grade you on your artwork unless it's so horrendous that it's incomprehensible. But, you know. So this is actually a multiple choice question, and the choices are the lighter car, or the heavier car, or choice C, the power is the same for both cars. Now, you might think that since they both start from rest, you just do force times velocity and they're both 0. In fact, you could also argue that the force on them is going to be the same, because net force on each car is going to be its mass times its acceleration, so ma for the first car, and then 2m times a over 2. The 2's cancel out, so it's ma for both cars. So force for both cars, force engine on both cars, equals ma equals 2m times a over 2 equals the same thing for both cars. Same force and same velocity of 0, so same power, right? Well, that's true, just at the very beginning. That's the instantaneous power. Right when they both start, right when the light turns green. And maybe that was the intention of the author of the book, is just how do their powers compare right when they start, in which case you would have chosen choice C. But the more interesting question to me is, what happens immediately after that first instant? Which car ends up having more power output over time? Which car ends up requiring more power from its engine over time? And that would have to be the first car, because while the force is the same for both cars, the first car is going to eventually reach a higher velocity. In fact, by eventually, I mean literally a fraction of a second after you hit go, after the light turns green. With a higher acceleration, it's going to reach a higher velocity immediately, and from that point forward, it will always have a higher velocity unless somehow this heavier car finds a way to increase its acceleration to catch up. But assuming no changes in acceleration, the lighter car is going to gain and keep a lead against the heavier car. It's going to have a higher velocity at all times except for time 0. And with that higher velocity, same force, it would have to have a higher force times velocity. It would have to have a higher power output from its engine in order to keep going. So that was more of a conceptual question than anything else, but I wanted to bring it up because I thought it was one of the better questions that I've covered with students over the years. And I think that is where we can stop for power. Now let's just take a look at general mixed review problems for the entire energy chapter and see what we can do. Let's see if we can find some good ones in here. I mean, I know we have good ones, but I can't tell you immediately. It's not like I have the problem numbers memorized. Although it does help for the ones that have figures. I can instantly recognize those. But the others, I might have to read through them first before deciding whether or not they're worth looking at. And it looks like we have a whole hour and a half, so... Well, I mean, I never said at any point that these sessions had to be exactly 3 hours per stream. But that's kind of what the average has been. So let's have a look. Okay, we kind of talked about this last time, but work done by a variable force, we talked about it a little bit when introducing the potential energy due to springs, elastic potential energy. But basically, they've got some graphs here of force versus position. So, let me see. This one says the force acting on a particle varies as in the figure, which I will draw for you in a minute. It says find the work done by the force as the particle moves from position 0 to position 8, and then from position 8 to position 10, and then from 0 to 10. So, what they have drawn for us is a graph, and on the vertical axis they have drawn F sub x, so the x component of the force in newtons, and on the horizontal axis they just have x in meters, position in meters. And they have, let's see, 2, 4, 6, 8, 10, 12. And then on the vertical axis, they've got, I guess the vertical axis goes down into the negative a little bit. They've got -2 and -4 over here, and then 2, 4, 6 in the positives. 2, 4, 6. My spacing isn't really that equal, but we will go with it. So it looks like we have a lowest point down there at 10, which seems to go around here. And yeah, that should all be a straight line. And then a straight line to here, and then that. Okay, so this is not curved, which means we can do it using algebra-based techniques. We don't need calculus. So yes, even Physics 1 students can be expected to have to do this. We already argued last time for why area under the curve for a force versus position graph can give you work. So let's see, they said find the work done from 0 to 8, work from 0 to 8 by this force. It would just have to be the area from position 0 to position 8. So just the area of this first big triangle over here. Okay, 1/2 base times height. So base is from 0 to 8, so that's 8. 1/2 times 8 times the height is going to be 6 newtons. So 1/2 of 8 meters times 6 newtons is going to be 4 times 6, 24 Newton meters, or 24 joules. Okay, so that's part A. Part B says find the work from 8 to 10. So now we use the area of this triangle, but wait a minute. Here, the force goes into the negatives. That would mean that the force is in the negative x direction, while the displacement is still in the forward direction. X is still increasing, implying that this object is still moving, let's say, to the right, while the force acting on it is to the left. Okay, so from 8 to 12, that's going to be a base of 4. So this is negative work from 8 to 12. Wait. Oh, wait, they wanted it from 8 to 10. Okay, my bad. They wanted it from 8 to 10, not 8 to 12. So actually, just half of this. So just that first half over there. Okay, glad I caught that in time. So that's going to be 1/2 the base from 8 to 10 is 2 meters, times goes down to -3 for the force. 1/2 times 2 times -3 is going to be -3, right? Half of 2 is 1, and yeah, -3 joules. And then part C, what is the work from 0 to 10? You can just now add these two. You can do 24 plus -3 and get 21 joules of total work done. The more interesting question they could have asked for part D would have been something like, if the initial velocity of this object was however many meters per second, then what will the final speed of this object be? And there you would just use your work energy theorem and say total work equals change in kinetic energy equals kinetic energy final, minus kinetic energy initial. And I guess you would need to know the mass of the object, so they would give you that in the problem, and that would be the end of it. And there we go. There's another problem similar to it where they draw a graph that looks more like a trapezoid. You could either use the area of a trapezoid formula, or you could chop it up into a square and two triangles, but we don't really need it. One example is enough for us. And what about this one? This one doesn't give us a graph, but it says the force acting on an object is given by F sub x is equal to 8x minus 16. That is a linear equation where x is in meters. And so yeah, for this, basically the same idea, except they gave you the equation, so you have to generate the graph on your own based off of that. And since it's a linear equation, it's just going to be a simple straight line graph. So once you draw it, you can calculate areas for it without needing calculus. But I am not going to do that since we've already kind of done an example of that last time when we were trying to derive the potential energy formula for a spring. It's basically the same kind of graph that we would end up with, except I guess it slopes up instead of down. Okay, let's look for some other problems. This one might be interesting. So it says two objects are connected by a light string passing over a light frictionless pulley, as in the figure, which I will draw for you. So they've got the ceiling, and then they've got a pulley hanging from the ceiling. And then more importantly, they have this. They've got one block over here and another block over here, and this other block is on the floor. So this block, they said, is M1, is equal to 5 kilograms in mass. And this block, they said, is M2, which is equal to 3 kilograms in mass. And they said this over here is a height of 4 meters. They called this h equals 4 meters. Okay. So it says the 5 kilogram object is released from rest at a point 4 meters above the floor. Part A, determine the speed of each object when the two pass each other. And then part B, determine the speed of each object at the moment the 5 kilogram object hits the floor. And then part C, how much higher does the 3 kilogram object travel after the 5 kilogram object hits the floor, assuming it doesn't bump into anything on its way up or exceed the length of the string, I think is something that they should have explicitly stated, but that's the implication I take from it, because otherwise that would complicate the problem beyond what you have enough information to figure out. Okay, we can do this. So part A, what is the speed of each object at the moment the speed of each object when they pass each other? So V1 and V2 when they pass each other. Just the magnitude. It said speed, not velocity, when they pass each other. I love how this is worded as if they think you're not going to realize that they have to move at the same speed when they pass each other. It's worded as if it wants you to find each one individually, which I guess could be a situation that can happen if they told us what the maximum tension is and we could calculate the exact moment when the rope snaps, if that maximum tension is exceeded, and then from there we could figure things out. But no, it's going to be the same speed for both of them. So once you find one of them, you've found them both. I can already say this: V1 equals V2 at all times. While pulley rotates. You'll understand the importance of those last three words once we look at part C. So yeah, determine their speeds when they pass each other. When they pass each other, how high are they going to be? Well, if this thing started 4 meters above the floor and this one started 0 meters above the floor, then when they pass each other is when they are each halfway. So that's going to be when this object has dropped 2 meters and at the same time this object has risen 2 meters. So that's going to be at the 2 meter mark. Okay, we can just use our mechanical energy equation here. We can say that kinetic energy 1 initial plus kinetic energy of object 2 initial plus potential energy of object 1 initial plus potential energy of object 2 initial plus the non-conservative work on object 1 plus the non-conservative work done on object 2 is equal to kinetic energy on object 2 initial, kinetic energy on object 1 final plus kinetic energy on object 2 final plus potential energy of object 1 final plus potential energy of object 2 final. I know, it's a lot of writing, and with enough practice, you'll be able to bypass a lot of this writing and just immediately substitute the things that are going to be zeros or combine the things that are just better off being lumped together. But while still learning, I think it is helpful to write it all out, just to train your brain to mentally check every item off the list. So initially the system starts at rest, so those are zeros. And I can set my zero height to here, so that's going to be my h equals 0 line. So that means that the potential energy initial of M2 is going to be 0. Okay, and then non-conservative work 1 and non-conservative work 2. So what non-conservative forces exist over here? We've got, well, first of all, what forces in general, conservative or not, exist here? We've got force of gravity acting on each block, and we've got force of tension. Gravity is conservative, tension is not. So let's see the work done by the tension. So the tension force should be equal on both of these in terms of magnitude. For M1, you've got that same force of tension up times a downward displacement of 2 meters. So that's going to be -2 force of tension. For block 2, you've got that same tension force up times an upward displacement of 2 meters. Those are in the same direction. That's going to be positive 2 force of tension. So negative 2 force of tension plus positive 2 of that same force of tension. These together are 0. Individually they're not, but together they are. It's just like that last problem we did in the previous stream. The total non-conservative work on the system is 0. Okay, and that leaves us with M1G H1 initial on the left-hand side. On the right-hand side, the final speed for both of them is going to be the same, so I can group these kinetic energies together and just do 1/2 m1 plus m2 times v final squared. I don't have to call them v2 final and v1 final because they're the same. So that's just putting those two together. And then for the potential energy, we've got m1g h1 final plus m2g h2 final. Okay. H1 final and H2 final both happen to be 2 meters here, so that's a substitution we can make. But yeah, let's plug in the numbers that we have. So we've got 5 times 9.8 times H1 initial was 4 meters. Block 1 started at 4 meters high. Equals 1/2, and then the sum of the masses was 5 plus 3, so that's 8 kilograms times V final squared, we don't know yet, plus M1G H1 final and M2G H2 final. I can group these together this time because H1 final and H2 final happen to be the same. So that's going to give me M1 plus M2 is 8 again, times 9.8 times 2. Okay, subtract this from both sides, so we've got 5 times 4 minus 8 times 2. 20 minus 16g would be 4g. So that leaves me with 9.8 times 4 equals the 1/2 and the 8 become 4. And the 4's cancel out, so V final squared is just 9.8, so V final is going to be the positive square root, since we're only looking for magnitude. Positive square root of 9.8 is about 3.13. I'm getting V final equals about 3.13 meters per second. Okay, so that's part A. Part B, determine the speed of each object at the moment the 5 kilogram object hits the floor. So part B, what is V final when M1 hits the floor? Okay, basically same equation. We can start with the same conditions that we had over here, so just M1G H1 initial for the starting point, and for the ending point, they're both still going to have the same kinetic energy at this point, so I can still do 1/2 M1 plus M2. I guess instead of calling it V final squared, I guess I should call it V bottom, just to reduce the risk of confusion with the previous part. So I'll call it V bottom squared. And then plus, this time M1G H1 final and M2G H2 final. The H finals for them are not going to be the same, so I am going to actually have to keep them separate this time. Cannot group these. M1G H1 bottom plus M2G H2 bottom, which is kind of weird to say because H2 is going to be actually at a higher height, not at the bottom, but maybe you guys can come up with better names for your variables than I did over here. Okay, so H1 bottom, it's just going to hit the floor, which we already defined as H equals 0, so good news is we've eliminated that from the problem. Okay, and then H2 bottom is going to be 4, so it's actually going to be the same as H1 initial. So these are both 4s, and those are both G's. So if I subtract this over to the left-hand side, then I can just rewrite it as M1 minus M2. So 5 minus 3. So yeah, that's what I'm going to do. Subtract this over to the other side, and I get 5 minus 3 times 9.8 times 4 meters equals 1/2 times M1 plus M2 is 8, and then V bottom squared. And let's see, 2 times 4 is 8, 8 times 9.8 is what, 78.4? 8 times 9.8, 78.4. So that's, wait, why did I even bother with that? 8 times 9.8, I can cancel this with these. Okay, and then multiply by 2, and you get 19.6 equals V bottom squared. Yeah, that would have been way easier. And then take the square root of that. Square root of 19.6. Square root of 19.6. I don't know how I missed typing that. Guess me 4.427. I'm going to say 4.43. V bottom is approximately 4.43 meters per second. And that's in scenario B. Scenario C, part C, it says, how much higher does the 3 kilogram object travel after the 5 kilogram object hits the floor? How much higher? Not to what height, how much higher? So after the 5 kilogram object hits the floor, the 3 kilogram object will be up here, and it will have an upward velocity of 4.43. And the question is, how much higher? So starting from here, how many extra meters? Not how high is it from the floor, just this. This is what they're asking. Be very, very careful with wording. And if you're not sure, you are confused by the wording and you're not sure whether they mean the height from the floor or the height from where it was at the end of part B, then you can do both. You can submit your answer as, let's say, for example, that the answer ends up being 12 meters. Then you would say the object reaches a height of 12 meters, which is 8 meters higher than it was when M1 hit the floor. And that way, you've kind of given both answers in one, and you can't be marked wrong for that. So yeah, pay attention to the wording of the problem. to make sure that you're actually answering the question that they are answering. And if you're not sure between one or two questions they could be asking, then word your answer in a way that covers both. Language. Now, what happens after block 1 actually hits the floor? Well, it can't continue going down, obviously, so object 2 will go up, and what forces will be acting on object 2 from this point on? What forces will be acting on block 2 from this point on? There's, of course, the force of gravity. What about that tension force? Well, that tension force is going to disappear because without M1 dragging the string downward and pulling it around this pulley, the rope will just go slack. It'll still be attached, but there isn't going to be any tension in it. It's just going to be completely loose. So gravity would be the only force acting on M2 from this point forward. So if I had drawn this as a bunch of separate scenes, I guess you could say, maybe I should... No, I'm not going to draw it. But you could say this is what? I guess scene 1 is the original drawing. Scene 2 is when they meet halfway at 2 meters above the floor. Scene 3 is when block 1 is on the floor and block 2 is up here. And scene 4 would be when block 2 has risen. Scene 4 I will draw would be something like this. So block 1 has been on the floor for however many seconds long. And here's the pulley. And here's the string from earlier. It's all bent and twisty because, well, it's slackened, it's relaxed. And we'll say that this over here was the original 4-meter height. I know I've kind of drawn it a little crunched up compared to what it was before. And yeah, basically, maybe if I had used up a little bit more of this vertical space, I would have been able to draw something a little bit more convincing that we could compare more directly to this. But this would be your scene 4, and then this is that question mark distance that I drew up here. Yeah, I kind of just took this and it's kind of vertically smushed. But hopefully you understand what I'm trying to illustrate with it. Now, one possibility that they didn't really account for here is that M2 could have been flung at a high enough speed upward that it could have gone all the way up and hit the ceiling over here before reaching its maximum height and then bounced back down. So we're just kind of trusting the author of the problem that that's not happening here. We kind of just have to trust the author to have thought about the problem carefully enough to create a height where, well, I mean, we don't even know the length of the string or how high above the floor this ceiling really is. But yeah, we're kind of just trusting the author of the problem to have accounted for that, and we're assuming their intention was that this second block, however high it rises, it's not high enough to pass over the height of the pulley by enough to hit the ceiling, because that would throw a wrench in our problem and we wouldn't really have enough information to account for that. So anyway, let's do the math. So now we can just completely ignore block 1. It's not going to do anything here. It's not going to do anything anymore because it's just sitting still. Now it's basically as if we just have block 2 rising from here to wherever here is. So we can say work non-conservative on block 2 in this scenario is going to be 0, and we can say kinetic energy initial plus potential energy initial plus that 0 non-conservative work equals kinetic energy final plus potential energy final. The kinetic energy final, if it's just moving straight up, then once it reaches maximum height, it should be at 0. There are no horizontal velocity components to account for that can't be canceled out, so this isn't one of those scenarios that I was talking about earlier where if somebody drives off a ramp at an angle, they can't reduce their kinetic energy to 0 due to not having horizontal forces. That's not what's happening here. You can get to a kinetic energy of 0 in this situation, and that allows your potential energy final to be as high as can be. So let's see, kinetic energy initial was 1/2 times m2 was how much? 3 kilograms times v squared. What was v squared over here? It was, well, v was 4.43, and we got that from square rooting 19.6. So v squared is 19.6. That's a little bit more exact, so I'll do that instead of squaring 4.43 on my calculator. Okay, and then potential energy initial, quote unquote, it's really potential energy at the end of, at scene 3. So that's going to be 3 times 9.8. Did I write 98? 9.8. 9.8 times the height was 4 meters here equals kinetic energy final, we already said is 0. Potential energy final is going to be m, 3 kilograms, times g, 9.8, times h final, we do not know yet. I guess I will call it I'll call it h top, since we haven't used that yet. I know, not really the most creative variable names here, but in the interest of time, I'd rather not dwell on it too much for now. Okay, so we can divide everything by 3 and cancel out the 3's, and we can divide everything by 9.8. The 19.6 reduces to a 2, and then the 2 times the 1/2, those cancel out and reduce to just a 1. So you're left with 1 plus 4, so h top is 5. So 5, where do I want to write this? I guess I'll write it over here. 5 equals h top. And that doesn't answer the question. 5 is the absolute height, but their question was, how much higher does it rise compared to where it was during scene 3? So during scene 3, it was 4 meters high. In scene 4, it reaches 5 meters high. So their actual answer that they're looking for is h top is 1 meter higher than, what was it? I guess we call it h2 bottom. That's what they're looking for. They're looking for this rise of 1 meter. They're not looking for the actual height that it reaches, at least based on the way the problem was worded. But again, if you want to play it safe because you're not sure, you could say that the block reaches a height of 5 meters, which is 1 meter higher than it is when M1 hits the floor. You can just write all that out in words, and then you'll be covered in either case. You'll have successfully communicated to the grader that you understand what's going on with the problem, and that's really all they truly look for free response questions. Okay, now we can flip to the back side of this page and start looking at something else. Okay, how about this one? So it says a 200 gram particle is released from rest at point A on the inside of a smooth hemispherical bowl of radius r equals 30 centimeters, which they have a drawing of. So they've drawn this bowl, which is a hemisphere. I haven't really drawn it really well. But yeah, that's more of a 3D drawing, and then the flatter drawing, I'm just going to draw a cross section of it like this. Okay, so they've got the block is released from over here. So it's released from rest at point A is what they called this. They called this point A. And then they said the radius of this hemisphere is 30 centimeters. 30 centimeters or 0.3 meters. And it's asking us if this thing is 200 grams, mass equals 200 grams, which is 0.2 in kilograms. It is asking us, for part A, calculate its gravitational potential energy at point A relative to point B, which they've marked over here. Point B they've marked as that. And then point C they've marked over here. Point C they've drawn is I guess I haven't drawn it really well, but it's supposed to be 2/3 R above the bottom of the bowl, where R is this 30 centimeters or 0.3 meters. So yeah, part A, calculate its gravitational potential energy at point A relative to B. Relative to B means treat B like the zero height. So I'm going to go ahead and do H equals 0 at point B. And then part B says calculate its kinetic energy at point B. Part C says calculate its speed at point B. Part D says calculate its potential energy at point C relative to B. And part E is its kinetic energy at C. Oh, okay. I guess this isn't really as exciting of a problem as I thought it would be. I thought there was going to be some fun geometry here, but okay, it really is just, man, they could have done so much better here. Oh well. We've already written everything down and drawn the diagram. We might as well just do the problem. So the things they want us to find are potential energy at A, actually I'll just leave, I don't know why I wrote that comma, equals question mark. We'll pretend that comma's not there, scribble it out. They want kinetic energy at point B. They want speed at point B. They want potential and kinetic energy at point C. Potential energy at point C and kinetic energy at point C. Those are the 5 things that they want. Shouldn't be too hard to do. So potential energy at point A relative to B, setting B to be your 0 height. They said this was released from rest. They already told us that VA is equal to 0. Now we just need to account for what forces could be doing work on this thing. So they said it was a smooth hemispherical bowl. Smooth means no friction. So forces acting on this thing would be normal force and gravitational force, and that would be it, because I'm assuming no air resistance as well. No friction, no air resistance, normal force, which is going to be that way when you're at this point. It's going to be when you're at this point, it'll be that way. When you're down here at the bottom, it'll be straight up. When you're over here, it'll be that way, and so on and so forth. And other than that, you have a gravitational force, which is just going to be straight down no matter where the object is. So the normal force is always going to be perpendicular to the displacement, because when you're up here, your displacement is straight down, so that's a 90-degree angle with the normal force. When you're over here, your displacement is going to be that way. When you're over here, you're going to be moving that way. When you're over here, you're going to be moving that way. So at all times, the normal force is perpendicular to the displacement from moment to moment, which tells us that the angle between them is 90 degrees. Work by normal force is always going to be 0. Work done by normal force, whoops, that should be a capital N. Work done by normal force equals whatever that normal force is times whatever that displacement is at any given moment. I guess I would call it delta S here, since it's not always fully in the x direction, times cosine of 90 degrees no matter what. So this is always going to be 0. And that means that our non-conservative work is 0, which means our mechanical energy is conserved. So I guess we can divide this into 3 scenes. Scene 1 when you're at point A, scene 2 when you're at point B, and scene 3 when you're at point C. And between all scenes, there's no non-conservative work being done at all. So if we wanted to write an equation between scene A directly to scene C, we could do that. Or we could just take steps and go from A to B and then from B to C. We could do whatever we want, since there's no non-conservative work being done between any of these stages. Okay, potential energy at point A. Pretty easy to do, just mgh. So potential energy at point A is just going to be mg times h at point A equals, what was it, 200 grams, 0.2 times 9.8 times the height, Well, if this is 0, then A is going to be at a height of 1 radius above point B, right? If the radius is 30 centimeters, then the distance from here to here must also be 30 centimeters, or 0.3 meters. So there we go. Multiply those out and you're done. So 0.2 times 0.3 times 9.8, 0.588 joules. Okay, kinetic energy at point B. Kinetic energy at point B. Well, if you know your mechanical energy well enough, then you might be able to immediately see that the answer is going to be 0.588 joules. You start with a potential energy of 0.588 plus a kinetic energy of 0 plus non-conservative work of 0 equals potential energy of 0 plus kinetic energy of, well, it would have to be 0.588 for that equation to work. So yeah, you can answer it immediately if you can do all that reasoning in your head, but if you can't see it in your head quite yet, then you can just do kinetic energy A plus potential energy A plus work non-conservative equals kinetic energy B plus potential energy B. Kinetic energy A is 0 because you start from rest. Potential energy B is 0 because we set the height to 0, and also something I haven't been saying all this time that we've been doing it. The potential energy that we've been dealing with in all of our problems today have been gravitational potential energy. If there was a spring potential energy, we would have to add that into our equation as well. But since we haven't had to do that, we are fine. And let's see, so that we already determined was 0, so potential energy A equals kinetic energy B, so 0.588 joules. You are done. So that is the second part. Then they want the speed at point B. Once you have the kinetic energy at point B, this is easy enough to do. VB can be determined by just doing 0.588, the kinetic energy at point B, equals 1/2 the mass times VB squared. 1/2 times 0.2 is 0.1, and then if you divide both sides by 0.1, that's 5.88 equals VB squared. Take the square root of 5.88, and we get about 2.42. We're getting about 2.42. VB is about 2.42 meters per second. And there's part C. Next, they want the potential energy at position C. Easy enough to do, we just do MGH. So I guess I will switch to red here. Gotta make sure that my entire page stays in frame. So part C, or part D rather, potential energy at point C is equal to M times G times HC is equal to 0.2 times 9.8 times, they called this height 2/3 R, 2/3 of 0.3 is 0.2. And there we go. We get, what is that going to be? I'll just use the calculator for this. 0.392, right? 0.2 times 9.8 times 0.2 Yeah, 0.392. In joules. And finally, kinetic energy at point C. It would just have to be 0.588 minus 0.392. Again, in case that's not readily apparent, we can do, I can compare A to C or B to C. It doesn't really matter. Let's do A to C. So kinetic energy A plus potential energy A plus the non-conservative work is equal to kinetic energy C plus potential energy C. Kinetic energy A is 0, work non-conservative is 0 between points A and C, and potential energy A we already determined a while ago was 0.588 equals kinetic energy C is what we're trying to solve for. Potential energy C we got in the previous part is 0.392. Subtract 0.392 from 0.588, and I believe that is 0.196. 0.588 minus 0.392. Yep, 0.196. So we get kinetic energy at point C is equal to 0.196 joules. And if they really wanted to, they could have asked us one final question. What is the velocity at point C, or what is the speed rather at point C? And we would have done something similar to what we did here. Set 0.196 equal to 1/2 of 0.2 times VC squared and solve for VC. But that is where that problem ends. So let's see if we can find another good one to practice with. Oh, this one might be informative. This is something I didn't talk about, another unit of energy that may come up. Yeah, I might want to do this one, but let me read some of the other questions first. That one might be worth it. Don't mind me just mumbling to myself. I will probably end up looking in my other book for more of these. I see maybe one potentially interesting one after this. But yeah, let's do this one. So it says energy is conventionally measured in calories with a capital C, as well as in joules. I mentioned that it's a capital C for a reason. I will explain in a minute. 1 calorie in nutrition is 1 kilocalorie. So I guess they're explaining it for me. So this is something you might run into, and that's really the whole reason I'm even stopping to do this problem. So 1 calorie with a capital C is equal to 1 kilocalorie, or what they like to abbreviate as a kcal. A kilo, of course, is 1,000, so 1 kilocalorie is 1,000 calories with a lowercase c. So, I don't know whose bright idea this was, but in nutrition, calorie with a capital C is 1,000 of the scientific calorie with a lowercase c. So, nutritional calorie versus scientific calorie. In case you somehow ran into the idea that a calorie, 1 calorie equals, well, I guess it depends on whether you're doing physics or chemistry. In physics, we say that 1 calorie is 4.186 joules. And in chemistry, you're usually taught that a calorie is 4.184 joules. It depends on, well, a calorie is defined as the amount of joules of heat that it takes to warm up water by 1 degree. But the problem is that it depends on what temperature the water is already at. So I think in chemistry, they do water at 25 degrees, whereas in physics, they measure it for water at 20 degrees, and that explains the difference between the two. But yeah, if you ran into this idea and then you tried to, measure the amount of energy that you were burning, say, on a treadmill or whatever, and the treadmill was telling you that you burned however many calories, and then you tried to do the physics of it, and you realized, wait a minute, doesn't this seem way off? Yeah, the reason it seems way off is because your calories burned reported by your exercise equipment, if you have that, it reports it in nutritional calories. And the calories that you see on like your cereal box or whatever packaging from whatever food you eat, that's in nutritional calories. That is in thousands of physical calories. Makes you realize that a joule is actually a pretty small amount of energy compared to the amount of energy that a human uses in a typical day. But anyway, reading through the rest of the problem. Oh, actually, before that, let me write the abbreviations. A calorie, of course, is also called a cal. 1 calorie can also be written as 1 cal, C-A-L, and 1 kilocalorie can also be written as a kcal. 1 kilocalorie can also be written as 1 kcal for short. So if you see those anywhere, now you know what they are. Anyway, energy is conventionally measured in capital calories as well as in joules. 1 calorie with a capital C in nutrition is equal to 1 kilocalorie, which we define in chapter 11 of the book as 1 kcal equals 4,186 joules. Metabolizing 1 gram of fat can release 9.00 kcals. A student decides to try to lose weight by exercising. She plans to run up and down the stairs in a football stadium as fast as she can and as many times as necessary. Is this in itself a practical way to lose weight? To evaluate the program, suppose she runs up a flight of 80 steps, each 0.15 meters high, in 65 seconds. For simplicity, ignore the energy she uses in coming down, which is small. Assume that a typical efficiency for human muscles is 20%. This means that when your body converts 100 joules from metabolizing fat, 20 joules goes into doing mechanical work, here climbing stairs. The remainder goes into internal energy. That's you heating up and eventually sweating as a result. Assume the student's mass is 50 kilograms. Part A, how many times must she run the flight of stairs to lose 1 pound of fat? Part B, what is her average power output in watts and in horsepower as she is running up the stairs? Okay, so, oh my goodness, that's a lot of conversion that we have to do. So this is just another exercise in dimensional analysis, really. I think I'm just going to leave this one for you guys to try out on your own. Let me just write down the numbers they gave us. So 1 gram of fat equals 9.00 kcals of energy. And of course, I already gave you 1 calorie is 4.186 joules, or 1 kcal is 1,000 times that, so 4186. You just drop that decimal point if you want to convert this to joules. What else did they say? Let's see. So we've got 80 steps per run, 80 steps per run of the stairs, and 0.15 meters of height per step. Whoops, I forgot the H there. Height per step. And what else did they give us? 65 seconds per run. 65 seconds per run. And they said the efficiency for human muscles is 20%, meaning that the body converts, for every 100 joules, 20 joules go into work. So 20% efficiency. Meaning 20 joules of mechanical, I'll just write it down here, of mechanical energy per 100 joules worth of energy released from burning fat. I guess I'll call it chemical energy. For 100 joules worth of chemical energy released is how I will word it. Oh my goodness, I see why. I've never done this problem with my own students before. At least, not as far as I can remember. And then the remainder goes into internal energy, which we don't have to worry about. Assume the student's mass is 50 kilograms. So assume a mass of 50 kilograms. Which is 110 pounds. That's already pretty light. I mean, what age is this student supposed to be? And how much weight are they trying to lose? That doesn't sound reasonable at all. I mean, this is a book for high school students, so I would assume... I don't know, ask a doctor. But yeah, and then the questions were, how many times must she run the flight of stairs to lose 1 pound of fat? So, how many runs to burn 1 pound of fat? And you can look up the pounds to grams conversion. Well, let me see. So 1 kilogram is approximately 2.2 pounds. And yeah, so that gets you your conversion from pounds to kilograms. And then from kilograms to grams, you just multiply by 1,000. So if you want something more precise than 2.2, I suppose you can still look it up in Google if you really, really want to know. And what was part B? What is her average power output in watts and in horsepower as she is running up the stairs? So that's the first question. That's part A. And then part B, I guess I'll write over here. Part B. Average power, at least on the way up the stairs, in watts, in joules per second, and in horsepower. And there you go. And that is something that you can have fun answering on your own time. I'm not going through that one. Just feels like more headache than it is worth, and I think our time is better spent on something else. And that something else is gonna be... I just came across this one. I think this might actually be my first time doing it. It says Jane, whose mass is 50 kilograms. Let me start with the drawing they gave us. So they have a drawing here of Jane and Tarzan. So Jane is over here. And it says Jane, whose mass is 50 kilograms, needs to swing across a river filled with crocodiles in order to rescue Tarzan. Wait a minute, 50 kilograms again. I guess I just don't know the average weights that adult humans are supposed to have. I definitely weigh more than that, and I'm quite thin, so I don't know what's going on. I think I know what I'm going to be Googling after this. Anyway, Jane, whose mass is 50 kilograms, needs to swing across a river filled with crocodiles in order to rescue Tarzan, whose mass is 80 kilograms. So that's going to be heavier than me. I guess it might have something to do with height. How much taller than me would Tarzan have to be in order for this to make sense? I'll think about it later. Anyway, Jane, whose mass is 50 kilograms, needs to swing across a river filled with crocodiles in order to rescue Tarzan, whose mass is 80 kilograms. However, she must swing into a constant horizontal wind force F on a vine that is initially at an angle of theta with the vertical. And they've got the figure, so here's Jane. And Tarzan is over here. there's a tree, which I'm not going to bother drawing. And then there's a vine that goes down to about there. And it is at an angle of theta with the vertical when Jane grabs onto it. So that's the angle theta. And then they've also got in the drawing, they've also drawn that it is an angle phi away from Tarzan. And they've also drawn that there's a wind force, F wind, straight to the right, or the east, or whatever you want to call it. So in the figure, it says D is equal to 50 meters. D is what they called the size of this gap. Capital D equals 50 meters. The force of the wind is 110 newtons. Force of the wind is 110 newtons. The length of the vine is 40 meters. Let me do that in a different color. How about orange? Length of the vine is 40 meters. So worst case scenario, they'd be 10 meters above the crocodiles over here. Hopefully those crocodiles can't jump that high out of the water. And theta is equal to 50 degrees. Theta is equal to 50 degrees. Okay, so part A says, with what minimum speed must Jane begin her swing in order to just make it to the other side? Hint, first determine the potential energy that can be associated with the wind force. Because the wind force is constant, use an analogy with the constant gravitational force. And then part B, once the rescue is complete, Tarzan and Jane must swing back across the river. With what minimum speed must they begin their swing? So nothing regarding that angle phi. I don't know why they even put it in the drawing then. But I suppose we're going to find out. Let's see. So, with what minimum speed must Jane begin her swing in order to just make it to the other side? And with what minimum speed must they begin their swing in order to make it back? So yeah, this wind is acting like a sort of sideways gravitational force, so you can come up with a quote-unquote potential energy that you can associate with it, because it is acting like a conservative force here. It is acting like a conservative force. Basically, if I were to rotate the page like this, well, there you have it. The wind is basically doing the same thing that gravity does. If you're swinging towards the wind or away from it, it doesn't even matter if you're not swinging directly towards or directly away from the wind. If you're swinging at an angle, the same thing happens that you get with gravity. All that matters is how far you travel, I guess in this case horizontally. Your horizontal displacement is the only thing that affects how much work is done on you by the wind. The vertical displacement is going to be perpendicular to the wind at all times, so no matter how you move vertically, it's not going to have an effect. So all you need to know is your change in horizontal displacement to get your work done by the wind. And of course, if you reverse direction, you're reversing the work done, because the only thing that's changing is the direction of the displacement, the direction of the wind isn't changing at all. So yeah, it does actually, in this particular case, have the properties of a conservative force. So let's see. I guess that means I would do kinetic energy initial plus potential energy initial, and my potential energy initial is going to be two potential energies, a gravitational potential energy and a wind potential energy, quote unquote, plus non-conservative work equals kinetic energy final plus potential energy final. So kinetic energy final, if we're just making it to Tarzan, then we should make it just barely with no kinetic energy to spare. So that should be 0. As for potential energy final, if we split it into gravitational and wind, let's see. So kinetic energy initial, we don't know yet. That's what we're trying to find so we can figure out the kickoff speed. Plus potential energy initial, we've got gravitational and wind. So in terms of gravitational potential energy, it's higher when you go further up and lower when you go down. I'm going to go ahead and set the 0 height for gravitational potential energy here. And for wind, basically, it's going to be higher when you're further up against the wind and lower when you're further down. So I'm going to say that the 0 of wind potential energy is over here where Jane starts. So that's going to be, I guess, my x equals 0 position for wind potential energy. So gravitational potential energy is going to be mg times h initial, gravitational force times initial height, and my wind potential energy is going to be my wind force, 110 times x initial. And then my non-conservative work. Let's see. Non-conservative work. So if we're treating wind as conservative and gravity as conservative, then, and if we're ignoring the normal force because we're just starting from the moment after Jane lifts her feet off the ground, then that would only leave the tension in the vine as our non-conservative force. We're ignoring air resistance. So tension in the vine would be our only non-conservative force here, and the force of tension is always parallel to the vine, which is always parallel to her displacement. As she swings, we did a similar Tarzan problem last time, so if you remember the reasoning from last time, just chop up this curved path into smaller pieces, kind of what we did with the bowl earlier today, actually. Right, at different points when you're at the bottom, the tension is going to be straight up while the displacement is going to be horizontally to the left. When you're somewhere up here, the tension is going to be that way while the displacement is somewhere that way, tangent to the arc of her path. So at all times, the force of tension is going to be perpendicular to the displacement at any given moment, which means there's no work being done by the tension. So no non-conservative work to be had here. Equals, we already said 0 for the kinetic energy final, and for the potential energy final, For the potential energy final, okay, so there's going to be some gravitational potential energy. It's not going to be 0. Yeah, it's not going to be 0. 0 is right here at the bottom of the swing, and Tarzan is a little bit higher than that, so that's what this angle phi here is all about. We're going to have to do some geometry to figure this out. Oh, goodness. So we're going to have 0 kinetic energy plus mg h final, whatever h final is, plus, after going against the wind, it's the same as rising up against gravity, we're going to have something 110 times x final. X initial, we can just set to 0, so that is gone. But yeah, we need to figure out what h initial and h final are. We're going to need to do some geometry for this. So if this is 50 degrees and that thing is 40 meters, then if I do 40 times cosine of 50, I will get, if I do 40 times cosine of 50, I will get this. That is my 40 cosine of 50. And that's not very legible, but we'll work with it. And then my 40 times sine of 50 degrees, if I continue drawing a right triangle over here, 40 sine of 50 is going to be this. Let me actually just put that into the calculator and get the number. So 40 sine of 50 is about 30.64. This is about 30.64 meters. And 40 cosine 50, might as well put that in right now. 40 cosine 50 is about 25.71. So this is 25.71 meters. So if that's 25.71, and the full length of this vine is 40 meters, then 40 minus 25.71 will tell me what this is. I'll draw it over here, since there's more space here. 40 minus 25.71 is 14.29. Is 14.29 meters. Okay, so that gives us how far we are from the lowest point, from our h equals 0 point when Jane starts, but she's not going to be at the lowest point when she reaches Tarzan. Tarzan is a little bit higher. So since I know this is 30.64 and I know this is 50 meters wide, I can subtract from 50. 50 minus 30.64 is 19.36. A lot of steps to this problem, but they are not particularly hard. A lot of it is just simple addition and subtraction. So that was 19.36. Is that even showing up on the screen? Yes, it is. 19.36 meters. Okay, if we know this is 19.36, then we know that that is equal to 40 meters times sine of phi. So 40 sine of phi is equal to 19.36, which means sine of phi is equal to 19.36 over 40. 19.36 over 40 is equal to sine of phi, so inverse sine of 19.36 over 40 is 28.95. Let me actually write that somewhere. I guess we have some space over here for me to write it. So 19.36 over the hypotenuse, there would be a right triangle over here. The hypotenuse of that triangle would just be the length of the vine again. So 19.36 over 40 would be equal to sine of phi. So just taking the inverse sine of that ratio. If I take the inverse sine, so first of all, 19.36 over 40 is 0.484. Inverse sine of 0.484, I'm getting 28.9 degrees. 28.9 degrees. So phi equals 28.9 degrees. Actually, I didn't even need to find phi. I could have just done Pythagorean theorem. But since I found phi anyway, we might as well just do 40 times sine of phi. 40 times sine of phi. Or no, not sine. 40 times cosine, rather. 40 times cosine of 28.9 degrees is about 35.02. 35.02. So that's 35.02 from here to here. I don't really have the space to draw it, but if it's 35.02 from here to here, then Tarzan's height above the bottom of the swing is 40 minus that. So 40 minus 35.02. This tiny little height over here is 4.98 meters. 4.98 meters. Okay, so finally, H final is 4.98. Whoa, that was a lot of work. But again, it's just the sheer quantity of work. It's not exactly the most difficult thing. It's just geometry. But if this is giving you trouble, then this might be a wake-up call to review some geometry skills. Okay, now that we know all of this, we can finally plug in some numbers here. So we had kinetic energy initial, we don't know yet. 1/2 m v initial squared plus mg h initial was at 14.29 plus nothing, I guess, equals mgh final is m times g times 4.98 plus 110 x final. If x equals 0 over here, then x equals 50 over here, because the width of the hole is 50 meters, as they told us. Okay, and we can plug in the mass, which was, what, 50 kilograms? So, let's see. 50 times 9.8 would be 490. So 490 times, I'm going to subtract this over to the right. So 490 times 4.98 minus 14.29. 490, or no, yeah, 490 times, parentheses, 4.98 minus 14.29 is negative 4561.9, and then plus 110 times 50. Plus 110 times 50. Okay, that's 938.1. So I'm getting 938.1 equals 1/2 times 50 times v initial squared. Okay, so that's 25 divided by 25. 938.1 divided by 25 is 37.524, and if we take the square root, just positive root, since we only need magnitude, we get 6.1256. I'm going to round that to 6.13. So for part A, V initial must be 6.13 meters per second. Okay, so that was part A. Part B, once the rescue is complete, Tarzan and Jane must swing back across the river. With what minimum speed must they begin their swing? So this time, we want V initial starting from this point. Starting from this point. So the mass will have increased, and because the force of the wind doesn't increase with their mass, it doesn't depend on their mass, that means that unlike the gravitational equivalent, we can't just have them start with the same speed that Jane had when she reaches Tarzan by the end. So yeah, we're going to have to do another one of these. Let's see if I can squeeze it all in here. So what do I want to call it this time? I guess this V initial I should have called V1. Yeah, I should have called these 1, 1, 1, 1, 1, 1, 1, and then the finals I should have just called 2s. Okay, yeah, that works. And so now we are looking at, I guess they would be 3 to 4. So I would write kinetic energy 3, kinetic energy 3 plus potential energy 3 plus a non-conservative work of, it's still going to be 0, so I'm just not going to write anything there, equals kinetic energy 4, which will be 0 because we're just trying to calculate the bare minimum starting kinetic energy for them to just reach back to up here, plus potential energy 4. Oh boy. So that's going to be a 0. And I guess we can treat them as a combined mass of, what was it? Jane was 50 kilograms, Tarzan was 70, right? No, Tarzan was 80. Okay, I guess I have enough room to write it up here. So their combined mass, 50 plus 80 is 130. So I'm just going to write a capital M. 1/2 capital M V3 squared plus their potential energy 3 is going to be wind and gravity. So it's going to be mgh3 plus 110 x3 being 50, equals their final potential energy is gonna be mgh4 plus 110 times their x4 is going to be when they're back here at x equals 0. So that's another 0. So subtract 110 times 50 and subtract mgh3 from both sides, and that should do it. So h4, which was 14.29, minus h3, which is 4.98. So take that difference and multiply it by big mg and subtract 110 times 50 from that. So 14.29 minus 4.98 is 9.31, multiplied by their combined mass is 130 times 9.8, and that's 11,860.94. Subtract 110 times 50 from that, so subtract 110 times 50 from that, and that brings it down to 6360.94. And 6360.94 is equal to 1/2 big M times V3 squared. So if I divide by 1/2 of 130, half of 130 is 65. So divide 6360.94 by 65, and I get 97.86. So I'm getting V3 squared equals 97.86. 97.86. And if I take the square root of that, again, positive root only because we're just looking for magnitude. No need to consider the negative root here. But I say that every time just so that we don't forget when we get back to problems where the negative root is a possibility worth considering that it's there. Gotta remember that square roots have two possibilities. So I'm getting 9.8924. I'm just going to round it to 9.89. So V3, I guess I'll write it down here. Part B, V3 is equal to 9.89 meters per second. Interesting that they have to kick off with a higher speed over here when they're going with the wind than when they were going against the wind. But the reason is because when they are going with the wind, they are going against gravity, and when Jane is going against the wind, she's going with gravity. So yeah, gravity just wins out against the wind. If we calculated mg for Jane alone, what is that? 50 times 9.8? That's almost 500. That's 490 newtons of force. That's close to 5 times, a little bit more than about 4.5 times the force of the wind. So this does make sense to me. It does make sense since they're going to be going against gravity. It does make sense that V3 would be bigger than V1. Not to mention the fact that there's more mass in the second trip since Tarzan's mass is being added. So yeah, there you go. That took longer than I expected it to. So much for looking for problems in the other book. Our time is pretty much up. So I guess, what do I even give you guys for homework? I mean, it's the end of a chapter, so I guess I don't really have anything to offer other than go back to some of these, especially this last one. Give it a few days so that you don't remember exactly what the solution was, and see if you can come back to it and do it again from scratch on your own. And just do that for any of the interesting problems that you run into while doing your own homework problems. And continue looking for problems in your book. If you don't have an assigned textbook from your school, of course, you can just use the OpenStax book that I link in the course plan. For those of you who are new here, the course plan is linked in the description. And I think that is it. Just, if you feel like you've got a good grasp of this, great. Maybe skip the basic problems, but continue to do, a challenge problem, kind of like this last one, once every week or once every other week, just so that you don't forget these sorts of things. And if you're good on all that, then I hope you're prepared for next time when we will start digging into the concept of momentum and collisions. We're probably going to finish that in just 2 streams because it is a pretty quick topic. We're going to need to remember things from energy and force and maybe even a little kinematics, but mostly energy and force. So yeah, make sure you've properly mastered all that before next week, and I think that is it. Class dismissed.